So here we have a definite integral, and this happens to be one of those definite integrals that you cannot find a formula for. In other words, we can't say what an antiderivative of sine of x squared is. It's one of those funny functions that doesn't have an antiderivative that can be written in any way except for an infinite series sort of way. Okay, so what we need to begin with is find an infinite series for sine of x, preferably somewhere in the interval, centered at somewhere in the interval from 0 to 0.5. Okay, so find a power series for sine of x squared centered somewhere in the interval from 0 to 0.5. Why do you want to center it there? Because again, the accuracy of your Taylor series is better if you truncate it and just use a partial sum near the center, right? So in this case, 0 happens to be there, and so we can use a Maclaurin series for sine of x. And remember, Maclaurin series is just a fancy way of saying Taylor series centered at 0. So let's recall what that guy is. Sum from 0 to infinity of -1 to the n divided by 2n plus 1 factorial times x to the 2n plus 1. Always remember what your radius of convergence is. In this case, r is infinity, so this formula is good for all x from -infinity to infinity. Okay? So by substitution, I'm just going to take this x squared there and substitute it into my formula here. So we get a Maclaurin series for sine squared. Sine of x squared is sum from n equals 0 to infinity -1 to the n over all this 2n plus 1 factorial. And now we've got x squared in turn raised to the power 2n plus 1. And this is going to be good for all x squared and -infinity to infinity. Again, just by substitution. I've written x squared everywhere there was an x in the previous thing I wrote. So another way of saying that is it's also good for all x. So how about we write this thing down here in a compact form, and I want to try and show you guys how to get the antiderivative here, sort of two ways, sort of in parallel. So let's first go for just calculating the antiderivative here. Find an antiderivative for sine of x squared, because we're going to need that to evaluate our definite integral, right? So if I do this guy, would be the same as finding the indefinite integral of the series here, essentially. So if I were to actually, write this guy out, it would look like this, right? We'd start off with an x squared. So we're plugging in n equals 0, right? So we just get back an x squared. My x's are going to go up by a power of 4 each time. And then I'm also going to need to alternate in sign. So now I'm going to have x to the 6th. And I need to start counting up by 2's in my denominator. The first denominator was technically 1 factorial. Now it's a 3 factorial, right? Okay, so let's go for a bunch more terms right here. X to 10 over 5 factorial, x to the 14 over 7 factorial. Oops, that should be a negative. Alternating sign as well. Okay, and yeah, dot, 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 dx. That's what we're talking about here, and we can go term by term. So I want to actually write down the antiderivative here. So this is a constant. Everything out here is a constant, 2n plus 1 factorial. That's just a constant because we're antidifferentiating with respect to the variable x, okay? So that's just, that's just a formula for like 3 factorial. That's just a number. And then we have to go up by 1 in the power here. So we're going to get x to the 4n plus 3 power. Yeah, we're going to divide that by our new power, 4n plus 3. If I want to stop right there and go over to say equals, then I can't quite stop right there because I haven't included a constant of integration. If you look at all these powers, if I plug in n equals 0 right here, my first power is going to be a third power, right? You could also see that over here, integrating, finding the antiderivative of the first term would be this guy. Its antiderivative would be x cubed over 3, right? So we need to have a constant here, and we typically put the constant first because it is the lowest power term in a power series, right? So now we're going to have plus 1 over 3 factorial, x to the 7th over 7, plus 1 over 5 factorial, x to the 11th over 11, minus 1 over 7 factorial, x to the 15th over 15, and so on. Okay, so that's how it would look working it out in formula form and actually written out. Because for instance, there are a number of ways that we could re-index this thing, it's called. So for instance, if I wanted to instead do a sum from k equals 1 to infinity, okay, then it would happen that k would need to be equal to n plus 1. Or in other words, n would be equal to k minus 1. Okay, so basically I'm just taking that and I'm saying I want to add 1 to it. So that's where I get this. N plus 1 is what gives me my k. And if I solve for n in that, then I get n is equal to k minus 1. Okay, so now by substitution, and be careful, if I put a k minus 1 right here, what do you get? It's going to be 2k minus 2 plus 1. So it's going to be 2k minus 1. Okay, up here, we're going to have a 4 times k minus 1, so that's going to be 4k minus 4. So, or in other words, 4k minus 1, because we've got a plus 3 right there. Same thing down here, 4k minus 1. All right, so you could also write it like that, you know, a lot of different ways that you can rewrite these things. Anyway, we've now got our antiderivative, and so let's go ahead and figure out our definite integral here. I'm going to say here that our definite integral from 0 to 1/2 of sine of x squared dx is equal to this guy. So this is my power series that I found by anti-differentiating above. I only need one antiderivative, so I don't need to worry about the c. And into this, we are going to plug in x equals 0 and x equals 1/2, right? And if you do this calculation, then it should be obvious that when you plug in x equals 0, you get a whole bunch of 0 terms. So all that we're left with is what we get back when we plug in x equals 1/2. And you can see what that's going to look like real easily, because this is up here what that series looks like written out. Okay, so I'm going to get back 1/3 times 1 over 2 to the 3rd minus 1 over 3 factorial times 1 over 7 times 2 to the 7th plus 1 over 5 factorial times 1 over 11 times 2 to the 11th, and so on. Right, that's what I get right here. Okay, so you know, if we were able to sum that and find the limit there, we would be able to evaluate this thing. Okay, but remember, we don't actually have we don't know what formula this is. That's why we're doing power series in the first place. So we don't have any other better method. We don't know what the sum of this is exactly. we don't have any better method than just approximating. Okay, so we're going to approximate this so that the error is less than 0.001. Okay. Okay, so we're going to want to be able to approximate the error now. So let's recall the alternating series estimation theorem. It states that if we have an alternating series is convergent by the alternating series test, then let's say the error in approximating this the full sum by the kth partial sum is at most the absolute value of the next term, or in other words, just a sub k plus 1. Okay, so if we can find when this guy first hits the required bound of being less than 0.001, then we will have it guaranteed. So let's figure out what our first few terms are there. Okay, so the series from above right here has the first few terms like this guy right here, right? That would be our, so A0 is equal to 1/3 over 2 to the 3rd power, or in other words, 1/24. And if I were to write that out in decimal, then it looks like this. And A1 would be 1/3 factorial times 7 times 2 to the 7th, which if I write out in decimal is approximately 0.000186. If you notice, this guy is already less than 0.001 that we were asking for right here. Okay, so that means the error in approximating the full sum by the first partial sum, 1/124th, is at most 1/3 factorial times that 7 times 2 to the 7th guy, which in turn is at most the required accuracy that we were after. So we're done. So essentially, we know that that integral is approximately 1/124th.